Okay, off we go. For those of you who just came in, don't forget about the attendance quiz and the attendance code. Canvas does seem to be operational again, so we're back in business on attendance quizzes. So again, time's running out. You got a minute or so left. So last time we were talking about integrals in a coordinate system. What's the big idea of integrals in a coordinate system? The big idea is that when you have a new coordinate system, let's say polar coordinates, you have these conversion formulas that you can choose to view as a function, and in fact it makes for a fabulous change of variables function, as it turns out. It's a really nice point of view. Not only is it a change of variables function, this is one of the best, one of the most useful change of variables functions. Okay, so with that in mind, rather than every single time we use it, reinventing the wheel, re-deriving the Jacobian determinant, reconsidering, hey, how am I going to arrange to be able to get rid of absolute values? We do this once, and then we remember, right? It's very, very well worth your time. Such an easy little formula to memorize. The stretching factor is just R, right? So easy. But it does come with a cost. Again, the very small, the low price, right, of you are only now allowed to use non-negative values of R. This is so that you can reasonably and fairly get rid of those absolute values, which of course is really, really nice. Okay, so with all of that noted, and then while I'm here, I'll point out, practically the same thing for cylindrical, practically the same thing for spherical, different geometric details, different formulas, different small price to pay, blah, blah, right? But basically the same ideas. So we saw that you can use polar coordinates as a change of variables, and here I kind of phrased this example in the usual way that we do change of variables, namely viewing our domain as an image by way of some function of a more desirable domain, thinking about the pullback, slicing up the pullback, just a regular old change of variables. And then we made the observation, you can see how to do slices in our theta world by looking at what's happening in XY world. You just have to slice appropriately. And so here we have that same example. We did all this last time, of course. Same example. You can even see underneath where I've scratched out, you can still see that there is a pullback domain. I am still doing a change of variables. It's just that everything that I need to see over here, such as, what do my theta slices look like, and where's the first one and where's the last one? All of that stuff you can also see over here in XY world. You can see where's the first one, it's right there. And where's the last one? Right there. So, it's really not, mathematically, it's not any different. I'm just making the observation. You don't have to draw this. Everything you would have inferred from having drawn this pullback domain, just inferred instead from over here. Right? So, it's not really different, but it kind of feels different. Okay. All right. And I think where we ended last time, we were somewhere in the middle of this example. I'm just going to start over and do this example again. Okay. So we have an integral. Let's see. The domain for our integral is the unit disk, like so. And we're going to do this, again, air quotes, in polar coordinates, just like we did the last example. And the big idea, we got our differentials here with d theta on the outside. I'll talk in a minute about how to decide which way to slice, dr, d theta, dr, d theta or d theta, dr, which should you do? More on that in a second. But we've got theta there, and this is what our theta slices look like. That kind of thing, right? And I think it's a pretty reasonable pitch that the first slice is going to be where theta is 0. And then theta kind of goes all the way around until you get to the last slice. It's going to feel like we're kind of going in the same, we're back to the same direction we had been. You're going to want to call that theta equals 0 again, but you got to keep in mind we've gone all the way around. As we've gone around, theta has been increasing the whole time. By the time we get to here, it's now 2 pi. Like so. What do you think? Everybody happy with that? All right, so there's our theta slicing. Now, as usual, we're going to fix a value of theta, and we're going to think about now r. And where does r start and where does r end? Well, we're going to start at that point. That's the origin. R is 0 at the origin. Again, you get some freebies sometimes. You've got to love it. And then r is going to end at that point. And there's the one we have to kind of think through. That point, the defining characteristic of that point is that it is on that curve. That curve is the unit circle because of what our domain is. The unit circle has the equation r equals 1. And so our last value of r is 1. Everybody with me? Okay, now again, you can, I suppose, I don't know why you'd want to do this, but if you did want to draw the pullback domain and then slice that up with, our more familiar looking regular old slices, you can, right? But it's just a lot easier to just see it from the picture that we already have. And that's what I strongly encourage. Okay, a couple of last little details before we go on. Don't forget your stretching factor. Such a big deal. The stretching factor is arguably the most multivariable calculus of all of the ideas that go into solving this problem. So if you leave it off, it's just a big deal, right? Now again, this is a glass half full, glass half empty situation. I encourage you to view this as a glass half full. When you get the stretching factor correct and inserted where it should be, right? I tend to view that as, okay, this is strong evidence that the student knows how change of variables applies in this circumstance and knows the particulars of what how that manifests for polar coordinates. And that's actually pretty significant. It's worth a lot of points. Depending on this and that, in the past, this has been worth as much as 5 points, which is a lot for a single letter, right? That's good money. So make sure to remember that. Make sure to get those 5 points, right? Again, glass is half full. This is an opportunity, right? Now, of course, the glass half empty take is, if I forget that one thing, then I lose 5 points. Okay, well, but much better to see this in the positive sense. Okay, so just make sure to remember it, and then it'll be easier to see the positive take. Okay, also, don't forget to convert the integrand. I keep missing see my hand is in the way as I do this. So don't forget to convert the integrand, the prior integrand. So now again, you can, I suppose, plug in x equals r cosine theta and y equals r sine theta. Or you can remember that we already know what square root of x squared plus y squared is and save yourself the trouble. It's, of course, the same either way. Okay, so look how much easier this integral works out, right? This is the iterated integral then that I have to deal with, and it's very easy to compute the antiderivative of r squared with respect to r. We get 1/3 r cubed, and it just goes down. Super duper easy. Everybody happy? Okay. All right, a few tips. How should you decide between dr d theta or d theta dr? And the answer is always do dr d theta. For all practical purposes. I did feel the need to say almost here, I mean, there are some highly unnatural and manufactured examples that I did go to some trouble one time. I don't know why, but I did manage to create an example where it's actually better to do it the other way. It was a weird example, and I don't think you're going to encounter such naturally in the wild. So it's close enough to just say, just always do DRD theta. Okay, second thing. Now this is a strategic point. When you're writing down your integral, right, so you write down your differentials, DRD theta, and then maybe you go ahead and convert that integrand, and then you start looking at your picture, and you start thinking about slices and ranges of values and first and last, and the geometry, and converting from polar coordinates, or excuse me, from rectangular coordinates to polar, whatever. Bunch of stuff to think about, and in the mix, it is shockingly easy to forget that stretching factor. I've seen it a million times. Right? So now, something I've noticed over the years is that the more of a big deal I make about something, the less often students make that mistake. So I know that I'm making a lot of drama out of a seemingly, oh my gosh, that's so easy to remember. I'm going to remember for sure, right? But honestly, you still might forget. Because there's so much other stuff going on. So my workaround on this, and I hope you'll find this useful, is to just go ahead and always write down the R at the same time that you write down your DRD theta. And I think this is actually pretty natural. In fact, you will never need the DRD theta without also needing the R at the same time. So why would we ever write these down separately? It doesn't make any sense from a strategic point of view. So I strongly encourage you to do this, and you don't have to, and ultimately I can't tell. Right? So it's not a requirement, but I think this will help this will help protect you from, the inner accident-prone person that we have inside of all of us, right? This is what I do to defend myself against my inner whoopsie. So I hope that's useful. Okay, next example. Here we have a weird domain. The domain here is this annulus, we call it. It's kind of like a ring. It's the region between two concentric circles. Like so. And on that domain, I want to compute this integral up here. All right. Well, now here's the clever move. At least a clever attempt would be to say, okay, I tell you what I'm going to do. I'll compute it on the whole disk, the whole outer disk, because that's a relatively easy shape. And then I will subtract the integral over this inner disk, because that's also a relatively easy shape. And it's tempting to say that green minus purple will give us the annulus that we want. It's a clever idea. Trouble is, it just doesn't work. And the reason it doesn't work is you got to remember, integrals as we have defined them here are only defined when the integrand is continuous everywhere, and not only is the integrand not continuous at the origin, it doesn't even exist at the origin. So neither one of these two new integrals that we've introduced exists as we've defined things so far. So this is kind of nonsense. Now you might be thinking to yourself, okay, that's all formalities and stuff. But I'll also point out we have an explosion happening at the origin, right? This is not a removable discontinuity. This is a massive spike type discontinuity, and so you could be thinking, okay, well I remember single variable calculus improper integrals. And that's true, right? It just turns out that in general, in multivariable calculus, improper integrals is a weirder conversation, and it's not as cut and dry as it is in single variable. So you basically can't do that either. So this is just a real dead end approach. Great idea, except it doesn't work. Okay, second idea. Use rectangular coordinates. And the problem, of course, is that you'd have to break it up into 4 separate chunks. And who wants to do 4 integrals? We were hoping to get out of this with only 1 integral. And not only is this 4 separate integrals, but keep in mind each one of these 4 is going to have square roots in the inner bounds, which means all 4 of these iterated integrals are bummers. Right? Everybody seeing? So neither one of these options is making me happy. Right? So let's see what polar coordinates does, and it's just awesome. In polar coordinates, this is super easy. Theta slices look like this. And what's the range of values? Well, we're going to go all the way around. So 0 to 2 pi. No big. The inner bounds, let's see, for a given value of theta, we're going to start R at that point, which is on that curve, which has that equation, which gives me that starting bound for R. And then let's see, we're going to end at that point, which is on that curve, which has that equation, which gives us that upper bound for R. What do you think? Does that make sense? Everybody happy with that? Okay. Now you can't tell from what's written, but in fact, when I wrote down the dr d theta, I simultaneously wrote down the r at the same time. Again, I strongly encourage you to do that. Again, you don't have to, but it's your risk. So decide accordingly. And then, of course, don't forget that you also do have to deal with the integrand. Now, here our integrand is unattractive looking integrand, but in polar coordinates, this simplifies really nicely. This is in fact just 1 over r, and so we've got to include that as well. And there you go. And of course, you can see this coming. That makes our new integrand super duper easy, being just 1. This is the world's easiest integral, and you can do it in your head, and the answer is 2 pi. Everybody good? Okay, here's another one. Not quite as convenient, but still pretty good. There's a nice trick involved in this example. It's kind of my primary motivation here. So we're looking for this gray, now green shaded region here. It's the part of one disk that is specifically not also in this other disk. Kind of a solar eclipse sort of a shape. And let's see here, theta, keep in mind, theta is always measured out of the origin, right? So a theta slice looks like that. And we think about first and last. Here's the first. Here's that first slice. What can I say about that value of theta? And sometimes you get lucky. Now, you can identify the curves and the equations and solve and compute theta. That'll work. It works fine. But here's the easier way to do it. And sometimes you get lucky like this. Notice that point is on this unit circle, which means that those two distances are both 1. And that point is also on this unit circle, which means that that distance is also 1, and we've got ourselves an equilateral triangle. And we already know the geometry on that angle that we're interested in here. What is the value of theta there? Well, the magnitude of that angle is pi over 3 because of high school geometry. Anybody see how that works? Be on the lookout for this kind of thing. I mean, I'm not going to say it happens like all the time, but surprisingly often. And it's definitely useful to kind of keep your eyes open for, good, fortunate geometry. All right. Now, of course, in this case, this point represents clearly a negative value of theta. So, negative pi over 3. And then on the other side, the upper bound, of course, that's a positive. Likewise with another equilateral triangle. And that's going to give you positive pi over 3. What do you think? Everybody on board? Okay, now don't forget to convert the integrand. That's just plugging in. And, of course, don't forget to write this all down all at once as a sort of a workaround to help you not forget that stretching factor that's going to be worth a lot of points. Okay. Everybody's happy? We'll move on to the next thing. Okay. This next one, gosh, I wish we had more time. This is a super cool example. I am not going to go through all the algebra on this one. It's actually ultimately something similar to a homework exercise that y'all may currently be working on. I think it's going to be due on this Sunday, if I remember correctly. Anyway, there are some neat things that happen when you have an integrand that separates as a product of two single variable functions, and you can kind of move things in and out of integrals, and you end up with a product of integrals. So those same ideas that y'all apply in that homework exercise will allow you to turn this integral into this integral here. So that I'm going to suggest y'all think through on your own. What's nice about this, it's a little bit weird, but this integral that we're ultimately trying to compute, best way to compute it that I'm aware of is to turn it into this double integral. Now, why on earth would we want to take a seemingly simpler single variable integral and rewrite it as a double integral? This seems like a bad plan. Right? We're just making things worse. What's nice about it is that if you then compute that double integral in polar coordinates, like so, and of course, don't forget that stretching factor, right? That stretching factor of r, then notice my integrand here is no longer e to the negative x squared, for which I don't know how to write down the antiderivative. But it's e to the negative r squared times r, which is easy to write down an antiderivative. You just have to do a u substitution. Right? So weirdly, it's strange how this happens sometimes, and there's many other examples in math of this sort of thing. Sometimes the best way to solve a problem is to first turn it into a harder problem. And sometimes those harder problems put you into a situation where you have a different collection of tools to work with that allows you to actually solve it. So anyway, it's a great example. And by the way, also not a manufactured example. This is a very natural integral to want to think about. If you're doing statistics, probability and statistics, e to the negative x squared is something called a normal distribution. Integrals relate to probabilities. This is actually a really important distribution, right? If you've taken Math 230 or Math 340. So this integral is actually quite important. And this is the best way to compute it that I'm aware of. Okay, moving along. Cylindrical coordinates, pretty much just like polar, right? Again, let's see here. Let me go back a few pages so we can point. Just like with polar, we're going to take our conversion formulas. We're going to view them as a function. We're going to note that could be interpreted as a change of variables function. We've already computed the Jacobian determinant. We've already made the observation that if I promise only to use non-negative values of r, then I could ignore the absolute values. So we've got an easy stretching factor, and we can play the same sort of games. It's really a lot like polar coordinates, just three-dimensional instead of two. So back over to here. Whoops. Here we go. And again, you can see what these slices look like without actually doing the pullbacks. So for example, theta slices, which look like this. If you're in the pullback space, if you had, drawn your pullback domain and were doing good old regular old slices in our theta z world, right? This is what a theta slice would look like. And, well, I already know what that looks like in XYZ world. So just remember, instead of doing the pullback business, which, effectively we're still kind of doing, we're just not bothering to write it down, you just have to do your theta slicing like this. Right? Just remember that we have this new idea of what it means to slice. We slice in the sort of cylindrical theta sense, like so, and don't forget your stretching factor. So let's do a couple of these. Now, some similar tips. Here, unfortunately, I do have to recognize there are actually two orders of the differentials that can be good choices, distinguished by always keep your dr and d theta together and in the usual order. And then the question is, do you put dz on the outside or do you put dz on the inside? Right, so these two of our otherwise 6 different options. If you confine yourself to only using these two, again, it's hard to come up with a circumstance where this will not be just as good as any other option. And many situations where these are dramatically better than other options. Okay, so those are your two choices. Again, don't trust yourself to remember this stretching factor, right? Go ahead and write that down at the same time. Again, you will never need dr, d theta, and dz without also needing that stretching factor r. So write it all down all at once. Yes, sir?
When we're writing out the stretching factor, do we have to specify, we're going to limit ourselves to positive values of r, or is that
you don't have to say it, but you just have to abide by that rule. So as long as your r's are all positive, then I'm going to take that as perfectly acceptable. Yeah, absolutely. It's a good question. Anybody else? Yeah, so again, my gosh, don't trust yourself. You are, I don't know. I don't trust myself. How about that, right? I know that I will 100% forget sometimes if I don't write it all down all at once. So I hope that will be helpful to you too. And now let's dive in. So we got an example here. I'm going to do this example first with dz, dr, d theta differentials. As soon as we're done with that, we're going to do it in the other order. dr, d theta, dz. I want you to see how both of them sort of look, right? But one at a time. So we'll start with this one on top. And let's see here. Our domain is this thing here, this upper half ball. So, all of that. Okay, and let's start with the usual process. We've got theta on the outside. What's a theta slice look like? A theta slice is, again, a half plane hinged on the z-axis, like so. What do you get? This is a geometric appeal. What do you get when you take this kind of a slice of this half ball? And what you get is something like this. Right, so that's our theta slice. That's a generic representative theta slice. So what's the range of values of theta? Well, I mean, again, now this is a geometric appeal. You got to see this from the picture, and yeah, theta goes all the way around, doesn't it? So 0 to 2 pi. What do you think? Anybody like that? Okay, cool. So now again, we fix a value of theta. Now we're going to think about our next differential, right? So R. So what do R slices look like? Well, our R kind of, if you will, goes out that way. So here's your first value of R, and then here's a few more values of R, sort of R slices, and then there's your last R slice right there. So we just have to now figure out what is R for those values. For the first slice is part of the z-axis. That's where R is clearly 0. So again, you get some freebies sometimes, right? So R starts at 0. Is that cool? Everybody's happy? The last slice, as we discussed, is there. And here's where we're going to capitalize on a nice little detail. The value of R at that point is, in fact, also a radius. Oh, I shouldn't have used green. Sorry. Is also a radius, and this is a ball of radius A. So that means R2 is A. Nice. Everybody happy? Okay. And then, for both theta and R fixed, so looking at this R slice of our theta slice, go to the next variable. Next variable, we're going to be interested in Z. Well, we're starting there, and again, sometimes you get freebies. Z is pretty clearly 0. That we're in the XY plane, so of course that's where Z equals 0. We're going to end there, which is on our sphere. And you can write down the rectangular equation of the sphere, but we need the cylindrical equation for the sphere because we're doing this integral in cylindrical coordinates. So flash back to chapter 1. Make sure you're good with this being the cylindrical equation for the sphere. And then let's see here. Let's be careful. I am looking for a z bound. So in this equation, I need to solve for z. And that gives me my z bound. Everybody happy? Well, one thing you're going to notice with all of these different, we got cylindrical coordinates and polar coordinates, and in a few minutes we'll be doing spherical coordinate integrals. The geometry is different. The process is kind of analogous. It's always outside in, determine the bounds, fix a representative, move inside, find the range of value. It's the same sort of strategy with just sort of different geometry, different kind of sort of the shapes of the slices. Okay. All right. And don't forget your stretching factor. So easy to forget. See how we were doing all this stuff with the bounds and everything? Super easy to forget that. So as you're writing down the differentials, write down your stretching factor at the same time. Why wouldn't you? Okay, now let's do it the other way. Here we go. Now doing our z slices first. Here's a z slice. Right? Constant value of z, still just a horizontal plane. So geometric appeal, that horizontal slice of our half ball now looks like that. So again, we got to think about first and last. Well, the first one is going to be down here. And again, sometimes it's just obvious. Right? That's in the XY plane. That is where z is 0. It's right there looking at us. That's nice. The last such slice up there, and again, we get kind of lucky. That value of z is also a radius. And so the last value of z is a. Everybody happy? Okay, we fix a z. We're going to look at this particular z slice. Now let's think about apparently theta. So what do theta slices look like? Now again, you got to remember this is we're thinking about what a theta slice from the pullback domain. What would that look like in XYZ world? And remember, it is a half plane hinged on the z-axis, and now geometric appeal. How does this theta slice intersect our existing z-slice? And the answer is that intersection is a kind of a little line segment like so. So we're sort of interested now in these sorts of slices. And again, the question of first and last. And again, geometric appeal. It goes all the way around. Does everybody see how those theta slices go all the way around that disk? Right? And so 0 to 2 pi. Everybody okay? Okay. All right. Now, so as usual, now we fix both theta and z. We're looking at that theta slice of our z slice. And now we look at r. And what can I say about r? We start where it's obviously 0. Freebies. I love it. We end at a point like that, which is on our sphere, which still has this equation. And here's where a lot of students mess up. Super easy to mess this up. A lot of students will look back and say, oh yeah, I remember when we were here and we already did that algebra, and shouldn't it be square root of a squared minus r squared? Plenty of students will write this down from having had this previous experience. And the important point is, that's what you get when you're solving for z, which is what we were solving for in that previous example. We are no longer solving for z, right? We are now solving for r. So you solve for r in this algebra, and you get square root of a squared minus z squared. Everybody happy? But don't step on that landmine. It's easy to mess that up. Okay. Okay. On to spherical. It's so much the same. So again, just for impact, let's go back to when we were first doing this business. And same deal, we have these conversion formulas, which we can view as being a function, which we can utilize as a change of variables function, for which we can compute the stretching factor once. And remember, you don't have to do this calculation every time. Oh my gosh, right? Just do it once. Now you should do it once. Everybody should do their once, right? So make sure to compute that. Make sure you get rho squared sine phi, right? And then furthermore, remember that just as long as I promise only to use the values of phi that I tend to cling to anyway, right? The easy values, the most natural, in geometrically intuitive choices for phi. Just stick to those, and if you do, these absolute values go away, and you don't have to worry about absolute values. So it's one of these weird situations of you have to be very careful to stick to exactly what you want to do anyway. And it's easy to then forget about it and say, well, why would I do anything different, right? So I'm not going to bother worrying about that. And then a weird situation comes up where you'd want to do something different, and you can get in trouble, and your bridge falls down. Right? So be careful. Make sure to remember that rule. And otherwise, be prepared to deal with absolute values. Okay. Yeah. Again, we just got to think about what slices look like. Kind of old news. We already know what theta slices look like, right? Perpendicular to the theta axis means a constant value of theta, and a constant value of theta looks like this in XYZ world. Now, things get a little weirder when you think about phi slices. Phi slices are something kind of like this, what does that look like over here in this world? Keeping in mind what we're looking at here is a constant value of phi. Remember, phi is kind of angle off of the z-axis, right? So a constant value of angle off of the z-axis will give you something that's like a cone. And here's where, that's, okay, weird. I am accustomed to I've got a kitchen full of knives back at home, right? And I can cut horizontally, and I can cut at various vertical angles. I don't know how to do that with a knife, right? That seems weird. Here's the good news. We're only going to do our differentials in one order. And in that one order, we're going to be doing our phi slices of a pre-existing theta slice, and the way that these slices intersect is in a straight line segment. Whew. Close one, right? I was, when I first saw this, I was like, oh my gosh, these are going to be some weird shaped cuts, and the geometric challenge is going to be unreal. Right, but conveniently, if you just keep the differentials in the right order, you never experience curvy cuts. Okay. All right. Okay, same tips and tricks. Always use this same order. D rho d phi d theta. I'm not saying it's always better than the other options. I'm saying the other options are never better than this. If you stick to this order, you'll never have a problem. Asterisk. There are some weird, unnatural, oddball examples that you'll never see in the wild. I suppose maybe this isn't the best, but it's not worth your time to worry about. So just always do them in this order. Likewise, when you write down those differentials, always write down your stretching factor at the same time. Write down this whole thing all at once, just so you don't forget, right? We all have a certain amount of inner scatterbrain. I know I do, and this will help to defend you against that aspect of yourself, right? So it's just advice. You don't have to do it, but I hope you'll find it helpful. And let's dive in. Okay, so our domain here is this ball. And let's see here. Notice, by the way, the center of the ball is not the origin. The center of the ball is sitting on the z-axis. The ball is actually kind of sitting on top of the xy plane at the origin. Is that cool? Okay. All right. Now we're going to do the slicing in the one order that we ever will. So theta slices first. There's how you make a theta slice. What do you get for this particular solid? You get this kind of half disc. There's our theta slice, and I hope this is a believable geometric assertion. It goes all the way around. 0 to 2 pi. Is everybody happy with that? Okay. Now we're going to restrict our attention as usual to a theta slice, and here's one of my little hacks. We're going to start thinking about phi values, and part of the problem is that what we're looking at here, we're seeing kind of a scant kind of picture of this theta slice, and angles don't look right. So for example, that right there would appear to be an obtuse angle. I mean, it's just at a casual glance, just the way it looks off of the page, that appears to be an obtuse angle. But of course, in the three-dimensional world that we are trying to depict in this picture, it's actually a right angle. So that's confusing, right? There's a source of confusion, and one way that you can avoid this problem, if you should so choose, you don't have to do this, but I sometimes like to do this to keep myself from getting confused. Just redraw that whole thing where you're looking straight on. sort of a head-on view of that theta slice. And now, what didn't really quite look like a right angle, straight up looks like a right angle. So you might find this to be geometrically a little bit easier to work with. Suit yourself, doesn't matter. But I like that. And so now let's think about what phi does. Okay, well, phi is an angle like this, right? Where does it start? Where does it end? Well, we're going to start there, where phi is 0. We're going to end here, where phi is pi over 2. What do you think? Everybody buy it? Okay, so sort of in between those two is where our phi slices, phi slices start off pretty big and then they get sort of shorter and shorter and shorter until they don't ever really quite fully disappear until you get down to the horizontal. Okay. All right. Oh, by the way, let me show you another common mistake that I see. Very common. Easy to do. Easy to whoopsie this. If you're in a rush or under stress or whatever the case may be, sometimes there's a temptation for students to kind of imagine phi or any angle in general as being measured off of the center of whatever you might happen to be looking at. Right? So some students will measure their phi, and I know they know better than this, right? But look, again, your bridge is going to fall down, right? So if you measure your phis like this, you're going to get 0 to pi. That is, of course, completely wrong. Right? Does everybody see why that's completely wrong? So you just have to hold yourself, be strict with yourself and make sure you don't allow yourself this little sort of sloppiness. Phi is always measured out of the origin. Like that. Not out of the center of what round thing you might happen to be looking at. And again, the reason I mention it is because I see it a lot, and the more I mention it, the less I see it. So, there we go. Okay, is everybody good so far? We're almost there on this example. Last thing to do is to think about this phi slice of our theta slice. So fixing now both theta and phi. And we want to think about the range of values of rho. Well, whoops, what's going on here? Oh, my thing dies at just a critical moment. So rho starts at that point, namely the origin. Rho is clearly 0. No problem. We end there, which is on this curve. What's the equation of that curve? Wait a minute, where did that curve come from? It's another easy to kind of get confused. That curve, recall, was just a redraw of that, which is part of the sphere. Right, so don't forget where your pictures came from as you develop your process. This is really just part of that sphere. That sphere, you have all the particulars. You can write down the rectangular equation based on those givens. And then chapter 1, how do you convert a rectangular equation into a spherical equation? You plug in the conversion formulas and you go through and you do the whole song and dance, and you end up with that. That's your spherical equation for this sphere, or said differently, this is the equation that describes this upper bound for rho that we need. And so it is in that equation that we want to solve for rho as a function of phi and theta, and there you go. Everybody happy? Don't forget your stretching factor. Easy to mess that up. Right there it is. Make sure to remember that. Last thing I'm going to say, and then we'll call it a day. Please take your pictures seriously. It makes a dramatic difference. Keep in mind there's two reasons for this. It's not just so that you It's not just as an assistance to yourself. We're not going to be looking just at what's right and what's wrong. We're going to be trying to get inside of your head and say, okay, what did you understand? What did you not understand? Right? So when you're making intrinsically geometric arguments like this, it's really hard to argue with a picture being a good way to describe a geometric thought process. So having a good picture is important for communicating your ideas, which again is what we're here for. So make it nice and big. No postage stamp pictures, right? Take some time, make clear pictures. Don't try to do it all in your head. Go through a revision process. You will make better pictures after you've failed and learned in previous attempts. And by the way, there's things to know. This is not a matter of inborn talent. Some people, yes, I'm totally jealous. Some people are just really naturally talented at drawing pictures. I'm not. I wasn't. Right? When I draw decent pictures, it's because I've spent years and years practicing. Now, you don't have to do that much, right? But you do need to learn the techniques and practice the techniques and get good at it. It will make a difference. Y'all have a good rest of your Wednesday. See you later.